Hello everyone, I'm Mona. Here we are together on the MTEXTILER channel to learn about types of yarn production systems, understand what they are, identify them, and develop the ability to recognize different fibers. So stay with me. The 4 steps of fiber identification are as follows. 1. What is fiber? 2. Categories of fibers. 3. Main properties of fibers. 4 types of yarn production systems. In this part of the training, we deal with the machinery used for producing yarn from fibers, and we aim to gain a comprehensive overview of all the production routes. Stay with me for this exciting section. Types of yarn production systems. These are the various systems and machines designed to produce yarn from fibers. We will explore what they aim to achieve and what structural changes or creations they use to transform fibers into yarn. When this transformation takes place, the resulting product acquires specific characteristics. 1. Intertwining of fibers. 2. Proper distribution of fibers in a cross-section. 3. Uniformity of fibers. 4. Proper tension. 5. Placing fibers next to one another. 6. Fiber alignment. By imparting these characteristics to the fibers, we can use mechanical systems to transform disordered and scattered fibers into yarn with excellent regularity and cohesion. In the next slide, you can see an overview of these systems. We have 2 main types of yarn production systems: filament fiber spinning system, staple fiber spinning system. Each system will be explained separately. In the filament fiber spinning system, there are 4 methods for producing fibers and yarn: melt spinning, dry spinning, wet spinning, gel spinning. We will examine the first 3 methods in detail. Gel spinning is used only for special applications and is not common. In the staple fiber spinning system, we study 2 categories of fibers: short staple fiber spinning system, fiber length less than 6 cm, such as cotton; long staple fiber spinning system, fiber length more than 10 cm, such as wool and flax. In the upcoming slides, I will show you which type of fiber, as learned in the earlier section, can be used in each production system. For the short staple fiber spinning system, the common techniques include ring spinning, compact spinning, air jet spinning, rotor spinning, and more. For the long staple fiber spinning system, the common techniques include worsted spinning, woolen spinning, and others. The systems written in black font will be examined in detail. The rest are included merely to provide a broader perspective, as they are used for specific applications. The main difference between these systems lies in the method by which the fibers are twisted together. Depending on the twisting mechanism different in each machine, the fibers take a specific position and path within the yarn structure. This twisting directly impacts the overall properties of the yarn. This is how the various systems differ from one another. Stay with us as we step into the fascinating world of yarn production. In this slide, we begin with an introduction to filament fiber spinning productions, and in the following slides, we will examine in detail the 3 filament spinning systems we mentioned earlier. In the filament yarn production system, granules with different grades, meaning different quality levels, are used. The grade of a granule depends on the quality of bonding, the type of bonding, and the nature of the molecular chains in the granule. This determines how the granule will behave in the production process after melting or dissolving in a solvent affecting its viscosity, flow characteristics, purity, and uniformity. You might wonder, what is the raw material for granules? It is petroleum. Yes, petroleum and various monomers derived from it provide us with different types of granules, such as polypropylene, polyester, nylon, etc. The grade of a granule directly impacts its quality as a fiber or yarn, making yarn production smoother and resulting in higher levels of purity. After granules, which are mainly used in melt spinning systems, we move on to wood chips and polymer solutions that are used in dry spinning and wet spinning systems. Why? Because the first system, melt spinning, is based on melting polymers. While some polymers have such high melting points that this conversion becomes uneconomical, others, like wood chips, will degrade upon exposure to heat. When such raw materials are introduced into their specific systems, the machine structure delivers interconnected filament fibers that can be in the form of continuous filaments. If multiple long filaments are arranged together, we obtain yarn. It's important to note that all three production processes mentioned in the previous slide deliver yarn in filament form. Finally, by using industrial cutting machines, we can shorten these long filament fibers to any desired length and then use them in staple fiber spinning systems, either mixed with other fibers or alone. In fact, after cutting long filament fibers to the desired size, they can serve as raw material for short staple or long staple spinning systems, allowing them to be transformed into yarn. In the following slides, we will go into these topics in detail. It is also important to note that in filament fiber and yarn production systems, we can use master batch or color solution so that colored yarns and fibers are produced right from the start. In this method, the color is incorporated directly into the molecular chains, giving it much greater durability and stability. However, achieving the desired shade in this process requires a high level of experience and skill, and there may be some raw material loss before reaching the exact target shade. In melt spinning, colored granules are used. In dry spinning and wet spinning, the solution made from these colored granules is applied. This approach is especially useful for fibers such as polyester and polypropylene, which have low hydrophilicity, are difficult to dye, and have limited permeability to water and other substances in their yarn or fiber form. In their molten or polymer state, however, penetration and bonding are much easier. Next slide, melt spinning system for filament fibers. Raw material, granules or flake form. Types of yarns produced by this system: PET, polyethylene terephthalate, nylon 6, nylon 6,6, PP, polypropylene, process. Polymer granules are melted and extruded through a spinneret. Output product: continuous filament fibers. Fiber characteristics: can be produced as smooth or textured, including crimped, bulked, stretched, looped. This slide shows a schematic diagram of the filament fiber production process through melt spinning. The granules enter the weighing hopper and then go into the extruder. Inside the extruder, there is a screw, which is very hot and constantly rotating. With this movement, the granules are gradually melted and given uniformity. At this very first stage, we can add colored master batches and mix them to the desired color ratio. After complete homogenization of the polymer solution, it exits through the spinneret, which is a metal component with numerous holes, each hole corresponding to a single filament fiber. The shape of these holes can be circular, triangular, etc., depending on the cross-section we want from the spinneret. The filaments exiting the spinneret are controlled by the airflow and rollers in the machine, quickly cooled and solidified. The solid filaments are drawn between the rollers, and after drawing, there can also be a controlled heating stage to stabilize all the fiber and yarn properties. After that, by means of winding rollers, the continuous filament fibers produced are wound onto a bobbin. At the end of this stage, or in subsequent stages, we can transform the yarn from smooth to textured similar to natural fibers and wavy through various texturing processes. Also, after production, we can cut them through cutting machines to obtain fibers of different lengths. In this slide, we see that both white and colored granules have the capability to be transformed into fibers. But it is interesting and important to know that polyester flakes, which are collected, washed, and shredded, can be used as raw material for producing filament yarns instead of granules. Of course, these types of yarns have their own quality characteristics and specific applications, but they are highly practical. In this slide, you can see filament yarn on a bobbin produced in color, as well as white wavy cut fibers and smooth cut fibers, which, after production, have been turned into this form from continuous fibers. After a general review of the fascinating world of melt spinning, we move to the next method, dry spinning, whose characteristics are as follows. Dry spinning system for filament fiber. Raw material, spinning dope, which is a polymer dissolved in a solvent. Yarns producible with this system: acetate, acrylic, spandex, elastane, and polymers are dissolved in a volatile solvent. The solvent evaporates as it exits the spinneret. The production process is toxic. In this method, polymers are dissolved in their appropriate solvent. And at this same stage, we can also add a coloring substance according to the requested shade to color the final yarn. The polymer solution passes through the spinneret, and thin filaments are formed. Each hole of the spinneret creates a filament. The solvent in which the polymer is dissolved rapidly evaporates after exiting the spinneret. In fact, the filament encounters warm or dry air, which leaves the strand in solid form. The filaments are drawn by rollers in order to align the polymer chains and obtain appropriate strength and flexibility. At the end, a controlled heating stage is carried out to stabilize all the yarn properties. The yarn is wound onto a bobbin, and this type of yarn can also, depending on the need, be cut, textured, twisted, or used directly for fabric production. Here you can see various bobbins of yarn produced using this method, as well as cut fibers intended for use in staple fiber spinning systems. Now we move on to wet spinning to examine its characteristics. Wet spinning system for filament fibers. Raw material, spinning dope, which is a polymer dissolved in a solvent. Yarns producible with this system: viscose, acrylic, spandex, and the polymers are dissolved in a solvent and directly extruded from the spinneret into a coagulation bath. Diffusion and coagulation. The solvent and non-solvent come into contact, causing the polymer to solidify. The production process is toxic and has a low production rate. In this figure, you can see the schematic diagram of the wet spinning system. In fact, these types of systems are sometimes installed in multi-story buildings or large spaces. Because the production of filament yarns, given the great length of yarn and the working space required for these machines, as well as for the machines we previously examined, is very space-intensive, and the fibers, at each part of the machine, undergo an important and complex process. As shown in the figure, the polymer solution is dissolved in its appropriate solvent, and again at this stage, if desired, we can add a coloring substance according to the required shade so that it is dissolved at the same stage and mixed with the polymer. After exiting the spinneret, the polymer, in the form of a filament, enters the coagulation bath, where the polymer precipitates and solid filaments are formed. The formed filaments are drawn by rollers to stabilize the polymer chains. Any remaining solvent that remains on the fiber upon entering the coagulation bath is washed off, and a controlled heating stage is also performed to stabilize the properties. The filaments are wound onto bobbins and are ready for subsequent operations, which may include texturing, cutting, twisting, or direct use in weaving. In this method, unlike dry spinning, where the solvent evaporates, the solvent begins migrating from inside the fiber toward the bath. The bath can usually be water or acidic alkaline solutions, and at the same time, bath molecules, which may be water or chemical compounds, enter the filament and replace the solvent. The liquid solvent removed from the filament can later be collected, recovered, and reused. In this image, you can see cut fibers and filament obtained from the wet spinning system. In this slide, we move on to the staple fiber spinning system. In this type of production process, any of the intermediate products shown in the image below along each arrow may be present, or, depending on the type of system, may be omitted. However, in the ring spinning system, which is one of the oldest and most basic yarn production methods, these intermediate products are the stages of turning fibers into the final product yarn, and each has its own dedicated machinery. Let's review together what these intermediate products are. A bale of fibers collected from farms, from animals, or produced in previous methods, explained earlier, where filament fibers are cut and packed in bales, enters the blowing, cleaning, opening, and mixing machines in the staple fiber spinning line. After these compressed bales are thoroughly opened and cleaned, they enter carding machines. In these machines, a uniform fiber composite, the web, is formed, and at the end, it is condensed into a sliver. These slivers are then drawn in drawing machines, becoming more parallel, blended, and fed to the roving frame machines. In the roving frame machines, drafting occurs, and we obtain roving. A small amount of twist is applied to the roving to give slight strength. After that, in the ring spinning machine, rovings are drafted and twist is applied. The ring machine delivers yarn wound onto an empty cone. Because the yarn in this form is not yet directly usable, it enters the autoconer machine to both eliminate defects and provide excellent joining between the tail end of the previous ring frame bobbin and the head of the new ring frame bobbin, so that we avoid problems in subsequent processes. Weak and soft points along the yarn that can cause rupture in weaving are also removed. Several meters of yarn wound around ring frame bobbin are joined together in the autoconer to form a yarn bobbin. We can dye the yarn bobbin itself, or, if we have colored fibers from the very beginning, produce colored yarn directly. For cotton and other natural fibers, the easier method and the one that ensures more uniform dyeing is dyeing the yarn bobbin, or the final fabric product. In this slide, we understood the core structure of the oldest yarn production method. Stay with me so we can learn more in this training. In this section, we examine the ring spinning system, which includes two types, carded and combed. The production base is the same as we reviewed in the previous slide. The combed type simply has one additional intermediate product to produce higher quality yarn. Now here, let's review the characteristics of the ring, carded, spinning system. Ring, carded, spinning system for short staple fiber. Raw material, staple fibers in single and blended form. Yarns producible in this system. Cotton, polyester staple fiber. Nylon, PA staple fiber. Acrylic staple fiber. Viscose staple fiber, or a mix of usual fibers. Machine sequence used in this system: opening and cleaning, mixing, blending, carding, drawing, roving frame, ring spinning, autoconer, output product, continuous filament yarn, single ply. The oldest spinning method, as shown in the schematic diagram, this production process is a continuous operating method, and defects at any point in the production line can challenge the entire system. Due to the high production speed, even the smallest flaw in the process can result in thousands of meters of defective yarn. Therefore, constantly checking the line and production process, which in the schematic looks simple, but in reality occupies several production halls in sequence, is essential. In this slide, you can see all the machines lined up in sequence. In the opening and cleaning section, compressed bales are opened and mixed. In this section, the bales are weighed. And, before entering the production line, samples are taken in the laboratory. The lab checks their average and effective fiber length, degree of maturity, and many other parameters that we reviewed in Section 3. The number of bales arranged in this stage depends on knowledge and expertise, and on analyzing the results of raw material tests, the final yarn product requirements, and overall production line review in terms of shade, dye behavior, and the type or breed of fibers we want to blend. Even raw fibers differ in degrees of whiteness, and shade control is necessary throughout the whole production line. Sometimes, among the cotton bales, several viscose bales are also placed in order to, with a suitable proportion for final yarn quality, and due to the longer fiber length of viscose, facilitate the movement of cotton fibers during the production process and reduce the risk of damage to the machines. Note that, for example, it is possible to use only one type of fiber, but classification can also be done based on price and quality. For instance, 30% high-quality cotton, 40% medium-quality cotton, and 30% low-cost cotton can be blended, so that in the end we have uniform yarn. One of the reasons for using this machine is to ensure optimal fiber blending and uniformity in the final yarn. It is also possible to use two different bale openers so that two types of fibers can be properly mixed. After that, in the next section called Mixing Sot Blending, these two fiber types are again mixed together. These two different types of fibers, which may range from very high to low quality once properly blended, can be combined in any desired ratio. The second machine, Mixing Sot Blending, has the primary function of mixing and cleaning the fibers. This machine is equipped with a sensor that can detect impurities and remove them from the yarn production flow by means of air suction. Additionally, debris traps are also present inside the mixing hopper itself to remove waste from the production flow. Up to this point, the fibers are in a tangled and irregular state. In the third section, we move to the carding machine, which feeds the fibers into a system with a large cylinder. The fibers are aligned on this cylinder, drawn parallel, and any remaining contaminants fall into the waste bins at the bottom of the machine. With each full rotation of the cylinder, a thin fiber layer is taken from the outer tray of the machine. And finally, a part called the coiler compresses this web of fibers together into a sliver, an intermediate product, which is deposited neatly and orderly into the cans of the machine. This allows convenient transportation across the factory and proper feeding into subsequent machines. To evaluate and monitor the performance of the previous two machines, this intermediate product, the sliver, is tested in laboratories. The next machine is drawing, whose functions include mixing fiber slivers and drafting several different slivers together so that the fibers become straight and parallel again, returning to the thickness of a single sliver. The number of carding and drawing machines depends on the production rate and the overall capacity of the production process in a factory, and is determined at the initial installation and setup stage. In the drawing machine, multiple sliver cans are placed side by side, and several slivers are fed into the drafting section. This process has precise and dedicated settings so that they once again become a single sliver. This operation also improves the distribution of fibers in the structure of the final yarn. The next production step is the production of roving, in which the fed sliver enter the drafting zone of the roving frame machine, and we obtain roving with a slight twist. This machine also has its specific structure, but in this part of the training, we will not focus on the exact structure and operation of the machinery. Our main focus is on the overall yarn production process. After that, in the next drafting stage in ring spinning, we reach the yarn fineness we desire, and the final yarn is wound onto the spinning bobbin. During this process, defects may also occur in the produced yarn. In the autoconer machine, in addition to removing these defects, we can unwind the yarn from the spinning bobbin and join it together in this machine so that in subsequent operations, there will be no breaks at these points, and the overall structure of the yarn will be well formed. Because these joints, if not formed properly, can also cause yarn breakage and lower production efficiency in other machines. As you can see in this slide, the yarn structure obtained from the ring, carded, spinning system for short staple fiber differs from other systems because the level of fiber interlocking and the way fibers twist around each other varies depending on the overall production process used. In general, for forming yarn in short staple systems, fiber entanglement and twisting around each other are essential to create the yarn structure. In this slide, we will examine the ring, combed, spinning system for short staple fiber, whose characteristics are as follows. Raw material, staple fibers in single and blended form, yarns producible in this system. Cotton, polyester staple fiber, nylon, PA staple fiber, acrylic staple fiber, viscose staple fiber, or a mix of usual fibers. Machine sequence used in this system: opening and cleaning, mixing, blending, carding, combed, drawing, roving frame, ring spinning, autoconner, output product, continuous filament yarn, single ply, combing, for removing short fibers and aligning the fibers, produces yarn with more twist and uniformity. Note, more waste and higher prices. In this slide, you can see the schematic diagram of the overall production process for this system. After carding, the combed process is used. Before combed, we can have drawing, and also after it as well. During the combing process, fiber slivers are separated, the fiber bundle heads are combed, and short fibers and waste are completely removed from the main fiber bundle, then joined again to the tail end of the bundle. This process continues at high speed every few seconds, constantly, just like the precise, rapid, and amazing pumping action of the heart showing us the fascinating world of yarn production. In this slide, all the base machines of the ring spinning system are present, and the process is similar to what was explained earlier, with the difference that the combing machine is added to this production line. In this production system, the final yarn cost is higher, and because finer fibers are separated, there is more fiber waste. The resulting yarn is finer with fewer protruding fibers. As you can see in this slide, compared to the ring-carded yarn, this production system provides more entanglement within the yarn structure. In this slide, we examine the features of the compact, carded, spinning system for short staple fiber. In this system, as in ring spinning, there are also two types, carded and combed. It is important to note that this system is also based on the same ring yarn production principle, but with a series of minor modifications to the ring spinning machine, it has been able to present a different level of entanglement and complexity in the yarn structure and, to some extent, address the shortcomings of the previous system. Now let's review its features. Raw material: staple fibers in single and blended form. Yarns producible in this system: cotton, polyester staple fiber, nylon, PA staple fiber, acrylic staple fiber, viscose staple fiber, or a mix of usual fibers. Advantages: higher uniformity and strength, with lower hairiness compared to carded ring yarn. Output product: continuous filament yarn, single ply. Modifications have been made in the drafting system and the twisting zone, resulting in significant changes in the properties of the produced yarn. In this slide, we can see the compact carded spinning system for short staple fiber. Its machine sequence is the same as carded ring yarn, with slight differences in the ring spinning machine, performing the same basic tasks. In this slide, we examine the features of the compact, combed spinning system for short staple fiber. It is similar to the combed ring system, but with the same minor differences in the ring machine. Features: raw material, staple fibers in single and blended form, yarns producible, cotton, polyester staple fiber, nylon, PA staple fiber, acrylic staple fiber, viscose staple fiber, or a mix of usual fibers. Advantages: higher uniformity and strength, with lower hairiness compared to combed ring yarn. Output product: continuous filament yarn, single ply. Modifications have been made in the drafting system and the twisting zone, resulting in significant changes in the produced yarn properties. In this slide, the machine sequence for compact, combed, spinning system for short staple fiber includes the combing machine and the slight changes in the ring spinning machine. Now, in this slide, we review the features of a yarn production system in which airflow pressure is used to create a different type of entanglement and twist in the yarn, called the air jet spinning system for short staple fiber. Features: raw material, staple fibers in single and blended form, yarns producible, cotton, polyester staple fiber, nylon, PA staple fiber, acrylic staple fiber with other fibers, viscose staple fiber, or a mix of usual fibers. Machine sequence: opening and cleaning, mixing, blending, carding, drawing, air jet spinning. Output product: continuous filament yarn, single ply. Air jet spinning produces yarns with lower strength and uniformity. In this schematic, you can see the overall layout of the air jet spinning system for short staple fiber, which uses the drafting system and airflow to deliver yarn with the desired fineness and count. The machine order shown in the diagram is as follows. Like the ring spinning system, here too, we start with the opening and cleaning section, where at different levels, fibers can be taken and blended together as previously explained. In the mixing blending section, the fibers are cleaned, and in the carding section, they are converted into a fiber web and sliver. In the drawing section, drafting, mixing, and even distribution of fibers in the sliver structure is performed. Finally, by eliminating the roving in the roving frame machine and the ring frame bobbin in ring spinning and the bobbin winding in the autoconer, the sliver is directly transformed into yarn and delivered on a full bobbin. Certainly, this yarn structure differs in terms of entanglement, strength, and twist compared to ring and compact yarn in both carded and combed types. It is true that the production path has become much shorter, but it is important to note that the parameters examined in textile laboratories for overall yarn quality reveal that, at certain points of the yarn, this system has many weaknesses compared to the two previous systems. Therefore, it is necessary first to understand the final end use of the yarn and the permissible limits for these control points to ensure precision in producing or purchasing yarn for the intended final product. In this slide, the overall yarn structure in the air jet spinning system for short staple fiber is shown. Laboratory testing can evaluate parameters such as uniformity, strength, twist, etc., and then decisions can be made accordingly. In general, the strength of this yarn is lower than ring yarn, but air jet yarns have less hairiness compared to ring yarn. In this slide, we move on to the production process of the rotor, open-end, spinning system for short staple fiber, with features as follows. Raw material, staple fibers in single and blended form, yarns producible, cotton, polyester staple fiber, nylon, PA staple fiber, acrylic staple fiber with other fibers, viscose staple fiber, or a mix of usual fibers. Machine sequence: opening and cleaning, mixing, blending, carding, drawing, open-end spinning. Output product: continuous filament yarn, single ply. Produces yarn with lower strength and uniformity at a lower production cost. In this system, centrifugal force and a rotating rotor send fibers to the edge of the grooved circular surface, and under controlled airflow, the yarn is formed. Here, too, the fiber sliver is fed, directly skipping the roving frame, ring, and autoconner to form full yarn bobbins. In this slide, the production process can be seen via the equipment chain: opening and cleaning, mixing, blending, carding, drawing, rotor, open end, spinning. This yarn has lower strength compared to ring yarn, and, generally, is not used for high-quality fibers. It is often intended for producing thicker yarns and does not have the uniformity of ring yarns. In this slide, the remaining spinning systems for short staple fiber are mentioned, which, simply due to different mechanisms, produce the same yarn product but with different parameters of quality, uniformity, strength, hairiness, etc. Their brief explanations are given opposite each system name: friction spinning, vortex spinning, zero spinning, self-twist spinning, twistless spinning, electrostatic spinning. In this slide, we cover an important point. You may wonder how plied yarns, 2-ply or multiply, are made, or how elastic yarns are produced. In the spinning systems we have discussed so far, yarn is produced as single-ply. But to create the above types, the coning machine is used to place yarns, or lycra side by side, with other yarns, and then in the twisting machine, they are twisted together to fix them side by side, increasing their strength by becoming multiply. Machine functions: coning positions multiple feed yarns, including lycra, side by side on a bobbin cone in preparation for twisting. Twisting applies twist to the yarns placed side by side, forming a core spun yarn with lycra or other core fibers. In this slide, you can see images of these two machines, which have multiple heads, and depending on production scale, many units of these machines may be installed in a factory. Next, we move to spinning systems for long staple fiber, which include the worsted spinning system and wool spinning system. Worsted spinning system for long staple fiber features: raw material, staple fibers in single and blended form, yarns producible, wool, flax, polyester, staple fiber, acrylic staple fiber, viscose staple fiber, with other fibers or mixes of usual fibers. Machine sequence: opening and blending, scouring, cleaning, carding, gilling, combing, drawing, roving frame, ring spinning, autoconner. Output product: continuous filament yarn, single ply, used for producing wool and worsted yarns, including blends with polyester, with acceptable uniformity. This system is very similar to the ring, combed, spinning system for short staple fiber, but because the fibers are longer, there are engineering changes in all machines, especially at drafting points, and the gilling machine is present to parallelize fibers and prepare them evenly for the next step, combing. In this system, the most common synthetic fiber used is polyester, blended in defined proportions with wool to make yarns with better hand feel and hairiness, known as worsted suiting yarn, most widely used for men's suits. Wool spinning system for long staple fiber features. Raw material: staple fibers in single and blended form, yarns producible, wool, flax, polyester, staple fiber, acrylic staple fiber, viscose staple fiber, with other fibers or mixes of usual fibers. Machine sequence: opening and blending, scouring, cleaning, carding, drawing, roving frame, ring spinning, autoconner. Output product: continuous filament yarn, single ply, used for the production of bulky and hairy yarns. In this system, thick and hairy fibers are preferred for winter garments. Other spinning systems for long staple fiber are also shown in this slide. Each has its own features and production path. We have now reviewed the machinery and fiber-to-yarn conversion processes. I hope you have learned a lot. In the next chapter, we will cover common yarns and their features. So don't forget to subscribe, ring the bell, and keep watching related videos if you want to learn more about the world of fibers and yarn.